let's discuss one more example of the application of Laplace type methods for the solution of the differential equation with linear coefficients. So here is our new differential equation, and we'll discuss this time. We'll discuss the example with the third derivative. So here is our equation. This time we'll be interested in the solution which is finite or bounded at x tending to plus and minus infinity. And we'll normalize the solution at the origin by the following condition. Right. So let's write down our p and q polynomials. So p polynomial, so it's simply t cubed, right? Because only the senior power doesn't contain x, as we see in our equation. So q polynomial is t squared minus 1. Right. So now we compute the corresponding integral. Okay, so this is a simple integral. Well, you can take it by splitting t cubed into the product of t squared times t, and then you substitute t squared with t squared minus 1 plus 1. So the result is quite straightforward. It's t squared over 2 plus 1/2 the logarithm of natural logarithm of t squared minus 1. Right, so let's write down our v function and z function. So first, v function. As you remember, it's simply the logarithm of this part, and yeah, times e to xt. So here it is. And the logarithm is turned into a square root. Okay, now our z function. Well, again, it's the same kind of expression, but divided by q polynomial, which is here. So z function is e to t squared over 2, this time divided by the square root of t squared minus 1. Right, so now we are ready to write down our exact solution in the form of linear contour integral. Right, so our solution is some constant a times the contour integral of e to xt plus t squared over 2 dt over the square root of t squared minus 1. So here it is. So half of the whole procedure is done. And now we need to explore the behavior of the solution, namely its asymptotics at positive and negative x. And to this end, we need to choose the contour. As you remember, the contour should be chosen in such a way that v function assumes identical values at the end of this contour. Right, so you see again, as before, we have this t squared over 2 factor in our exponential function. And at large t, it dominates over xt term. Right, so that means it's very easy to find regions in the entire complex plane of complex variable t where v function vanishes. Well, first we have these 2 points, 1 and minus 1, where v function vanishes. Also, we have entire regions. So there are lines with the slopes of 45 degrees where v function vanishes. Okay, so let's shade these regions. All right, so now as you see, also v function is a multi-valued functions of t variables, so we need to choose branch cards. Well, this square root actually allows us to choose a finite segment as a branch card. But usually in most cases actually, this case is rather exceptional, but in most cases you don't have this simple square root, so you have some t squared minus 1 in some arbitrary power, right? So this finite segment branch cut is no good. So keeping this in mind, let's choose the most general form of the branch cut. So they are semi-infinite segments, and well, I don't know, it's actually not especially relevant, but let's show them directed upward, going upward. So this is the first one, and the second one is here. Well, of course, it's not a coincidence that I chose them going upward. It's actually very suitable, and you'll see in a second why. Well, now we need to choose the contours of integration for our exact solutions. Well, we have a third order differential equation, so there must be 3 linear independent solutions. And so what would be their 3 independent contours? Well, since we have these regions where the contour should start and end, and we have these special points actually where the contour can also end, because these are the points where the function vanishes. Well, let's actually, probably the easiest possible choice would be, this is going to be the first contour, why not? C1. This is going to be like the second contour, C2, and this will be our third contour. Right, as you see, they can't be smoothly deformed into each other because our branch cards prevent them from doing this. So they indeed define linear independent solutions of this differential equation. So let's investigate the asymptotic over the, for example, the left-hand side contour. So the asymptotic of the solution, which is defined by this C2 contour. Right, so yeah. So this is our Laplace type integral, and let's investigate its behavior when x is positive and large. So we are interested in bounded solutions. So here is our lambda parameter, which is large, and this is our f function. Again, the f function is not factored, so this large parameter is not factored out from our f function, but it's not that important, so let's write it down as a whole. So let's look for the possible saddle of this function. So we differentiate it. And here we go. There is a saddle at t equal to minus x. The second derivative is independent of of x. Sorry, it's simply 1. Right. So, and you can write down by yourself the equation for the steepest descent direction. And what you're going to get is just a very simple thing. It's alpha is equal to pi by 2 plus pi n. Right, so this is the steepest descent direction. So suppose x first is positive. Then our saddle is situated somewhere here. Right, and our contours, well, the most crucial part is that they should start and end at these shaded regions, right? So we can move them freely in the complex plane as long as it starts here and ends there in the upper complex plane. So we can simply shift our C2 contour to the left, and so it passes through this saddle. And as you see, we don't even need to deform the contour because it's already positioned in the steepest descent direction. So this is our shifted contour. And we simply just use standard Laplace type formula for the asymptotics of this integral. Right, so here we go. Y of x. So let's call the solution y2 of x. Now is equal to a times the square root of, okay, it's so it's 2 pi, right? And then so now we need to find the value of our exponential function, and t is equal to negative x. So it's minus x squared plus x squared over 2. So it's e2 minus x squared over 2, right? And finally, we need to figure out what the value of our multivalued function is, square root of t squared minus 1. By the way, let's actually use special notation for this function. Right, so to define its value at negative x point, we need to fix the regular branch for this function. So we fix it by the condition that if t is positive, large and positive, the value of this function is also large, or sorry, is also positive. So it's a simple arithmetic root when we go to plus infinity in this real t direction. So then if it's positive here, and we need to find the value of this g function here, we make a like pi rotation, as you see, in the counterclockwise direction. So the change of the argument of t minus 1 is minus pi, and the change of the argument of the complex number t plus 1 is again pi. So the full rotation is 2 pi, and g of minus x is actually equal to square root of x squared plus 1 times, minus 1 times e2 minus I pi. And approximately, since x is large, it's minus x. And here we go. So now finally we have our asymptotics at large and positive x. So this is this function divided by x. So now we need to investigate this. So it satisfies this condition. So it's bounded at large positive x. Now we need to check if it's bounded at large negative x. And so here we go. Let's address this question.